So I have a normal distribution here. Along the x-axis, I have x. Along the y-axis, I have f of x. F of x is the probability density function for the normal distribution. Okay. Yeah. And we have x. This point is x, and the adjacent point is x plus dx. Then the area fx dx. What is fx dx? So fx dx is approximately this area. Okay, so this area is approximately f of x dx. So the area fx dx, it gives the probability. This gives the probability that the measurement x taken at random from the distribution will be in the interval x and x plus dx. So what does it say? When I perform the experiment and take the measurement, then this expression gives you the probability. Okay, this gives you the probability that the measurement will lie between x and x plus dx. Okay. So what have I shown here? I have an experiment in which we take a particular measurement repeatedly a large number of times. And the error here is assumed to be only random errors. So when we plot the values of the measurements along the x-axis and the frequency of each measurement along the y-axis, we get a normal distribution. Okay. And this curve, normal distribution curve, is given by f of x. Right? We already saw the expression for f of x, and what was that expression for f of x which we saw? That f of x was 1 by root over twice pi sigma e to the power minus x minus lambda whole square divided by twice sigma square. This is the expression for f of x. Here lambda is the mean value of the distribution. Sigma is the standard deviation of the distribution. We already saw this. Okay, so to this f of x, if I multiply by dx, and what is dx? Dx is the distance between x and x plus dx. So what does fx dx give? fx dx gives that the probability that when we perform a measurement, then that value which we obtain will actually lie between x and x plus dx is given by f of x dx. Okay. So this function f of x is called a probability density function. Then what does the area fx dx from a to b give you? What does this area give? This area therefore gives the fraction of measurements falling in the interval a to b. Okay, so what does this area give you? It gives the fraction of measurements falling in the interval a to b. Okay. Falling in the interval a to b. This gives us the fraction of measurements. Or in other words, in terms of probability, this integration gives us the probability that when we perform the measurement, the value lies between a and b. A ga b ga marak sida laigani haibagi probability do sigi integration jana p. So this interpretation enables us to calculate the value of the probable error. So there is one term which is called probable error. Okay. So let us look at what probable error means. So what is the meaning of probable error? Okay, so probable error, how is it defined? It is defined as, so let me write down the probable error. The probable error is defined as the value of x, as the value of x such that, as the value of x such that one half of the observations or readings lie within x of the true value of the true value. Okay. So it is this. Yarwa. So I repeat, the probable error is defined as the value of x such that one half of the observations, that is readings, lie within x of the true value. Okay. This is fine. Do very good. So let me let us calculate the probable error. Okay. Aduna, let us consider a Gaussian curve. Okay, a Gaussian distribution given by, so let me use a different color now. Let us consider a Gaussian distribution. Yeah. Let us use a Gaussian distribution given by f of x equal to h pi root over pi e to the power minus h square x square. There you go. Here, if you compare this h with this value here, you can easily determine what h is. Okay, you can compare this and this, then you can easily determine what is the value of h that I am talking about. There you go. And then for simplicity, I have taken this lambda to be 0. Okay, so probable errors in a Karihare, the probable error is defined as the value of x such that one half of the observations lie within x of the true value. So here in this curve, this point is actually the true value given by lambda. Yareko, true value lambda ni, adudagi probable error ki definition the Karihare, it is defined as the value of x such that one half of the observations reading lie within x of the true value. So what do we have here? If I move a distance p from the true value towards the right, this will be lambda plus p. And if I move p value towards the left, then this point will be lambda minus p. So this will be lambda minus p. So lambda plus p, lambda minus p. Then it simply means that the area of this curve, the area of this curve between lambda minus p and lambda plus p is half now. Okay, so this is the definition of probable error. The probable error is defined as that value of x such that one half of the observation lie within x of the true value. So what have we taken that value of x? Here we have taken that value of x as p. So aduna habiti kaino lambda plus p amasung lambda minus p hariba sigi ani sigi marakta leriba sigi curve sigi area se, if this area is equal to half, then this p is the probable error. Okay, p is the probable error. and this P will be related to the value of sigma. Okay. So if sigma is small, curve is minus up. If sigma is large, the curve will be broad. This P will actually depend upon sigma, which is the standard deviation. And for simplicity, in this particular expression, I have taken lambda to be 0. So I have shifted my origin. To lambda. Okay, just for simplicity. So the area under this curve, then it will be given by 1 by 2. The area is equal to half, and it is so if we integrate this, so this will be integration fx dx from minus p to plus p. This is actually from lambda minus p to lambda plus p, and for simplicity I have taken lambda to be 0. Okay, so this when I substitute this is h by root over pi integration from minus p to plus p e to the power minus h square x square dx. And this is so this integrand, it is an even function. Therefore, this integration, this will simply be twice h root over pi from 0 to p. Here we have integration from minus p to p, and since the integrand is an even function, so I reduce the interval from 0 to p, and we have the factor of 2 here, and this is e to the power minus h square x square dx. Okay, and if you look at this carefully, I can do some manipulation. So I can take h inside, so I can write this as 2 by root over pi integration from 0 to p e to the power minus h square x square d of hx. I can write it like this. Okay, then maybe I should use the next page. Okay, I'll continue here. So if I change my variables, I can change my variables from x to u in such a way that h times x here, hx, this hx, here also we have hx. So if hx, if I write it as u, okay, if I replace hx by u, then this integration, this equality is given by half is equal to 2 by root over pi integration from 0 to, sorry, okay, I think I should use my next slide. This will be much better. So when I change my variable from x to u, what do I get here? So let me write sheet of paper. So when I change my variable from x to u, the integration becomes 2 upon root pi limit from 0 to, here I'm writing hp. Sorry. Here it's, let me write it hp. Okay, limit hp e to the power minus u square du. Okay, fine. So the earlier integration which we had, what was that? This integration. This integration reduces to the new expression. What is this new expression? This new expression. And we already know that this is the probability that when we perform a measurement, the value of the measurement lies between minus p and plus p. And according to the definition of probable error, this would be equal to half. Okay. So if we look closely, what is this left hand side? this left hand side is nothing but the error function. So this is nothing but the error function of HP equal to half. Here H is a constant depending upon the value of sigma. So H depends upon sigma and P is the variable. So if we look at the curve for the error function, we saw something like this. This value was 1. This was x. So half would be somewhere here. So this point. So this is half point. So this is the value of x which we need. So this gives us HP. Okay. So this is half. So half from the curve of the error function. This is the error function ERF. This is the error function of x. This is the error function x. Okay. So this point is 1 and this part is half. Okay. So CG point CG corresponding x-axis, this gives us the value of HP. So from graph or from the table of integrals, we obtain this value, and this value is actually HP is approximately equal to 0.4769. 4769. From this, we can determine the value of P, and P is actually 0.4769 divided by H. And then as I said, there is a relation between H and sigma. So let me come back to that. This is the expression. This is the expression for the Gaussian distribution. And this is the same expression for the Gaussian distribution when lambda is 0. So if I take lambda equal to 0 here, so what is now H? H kita. From this also you can see what is H. H is 1 by root 2 pi sigma. Okay, so if you compare this and this, you'll find that H is actually, so let me write it here. So here H is actually 1 by root 2. There will be no pi out, right? 1 by root 2 sigma. So this is H. Okay. So H is 1 by root 2 sigma. How do you know? You compare this and this, and you can easily find that H is 1 by root 2 sigma. So, so if I substitute H equal to 1 by root 2 sigma here, okay, then I'll find the probable error. The probable error in terms of sigma, this is equal to 0.4769 divided by, what is H? H is 1 by root 2 sigma. So this is actually 0.4769 multiplied by root 2 multiplied by sigma. And this value is approximately equal to 0.6745 sigma. Okay, so this is the value of the probable error. Okay, so I repeat, this is the value of the probable error. So standard error standard error is sigma, and now the probable error is 0.6745 times the sigma. So this is how we define probable error for a normal distribution. Okay, then I want to make one last point here, and then we'll stop. And what is that? So let me open a new slide, new whiteboard. Okay, and let me draw the diagram again. This is my x, y-axis, my x-axis. I have the normal distribution curve. This is x, this is f of x. We have the normal distribution curve. Okay, and see the midpoint, oh sorry, this point, the point where f of x is maximum, this is the mean of the distribution, which is given by lambda. Okay, this is fine. So we have this normal distribution. Let me use a different color here. Okay. So we have the normal distribution given by f of x equal to 1 by root over twice pi times sigma e to the power minus x minus lambda whole square divided by twice sigma square. This is it. Now, what is the probability that a measurement will fall within t times sigma of the true value lambda? I repeat, what is the probability that a measurement will fall within? So let me write it here. Probability that a measurement will fall within t times sigma, where t is some positive number, okay, some factor of sigma of the true value or the best value. And so I give the true value or the best value called lambda. It is given by the mean value. So the probability that a measurement will fall within t sigma of the true value lambda is given by so p within t sigma. P within t sigma is what did we saw? What did we see there? It was actually f of x dx from lambda minus t sigma to lambda plus t sigma. Siniko kung sa high give down. The probability that when we perform a measurement and the value of that observation, it lies between a to b, a and b. It lies between a and b is given by integration fx dx, where a is the lower limit, b is the upper limit. Adu hai gitna ko. So adu ko apply tawre. Apply tawre ka krai tawre. Agi lambda hariwa agi true value natraga best value sigi yet lambda t times sigma along. So you go t times sigma towards the right, and you also go t times sigma towards the left. So this point will be lambda plus t times sigma. This point will be lambda minus t times sigma. So when we perform a measurement, what is the probability? What is the probability that the measured value lie inside this range? See, range is the probability to can. What is the probability that the measured value lie inside this range? And that probability is given by the area under this curve. So that is given by the area under this curve. And that area under this curve, mathematically, it is given by this expression. Integration fx dx from lambda minus t sigma to lambda plus t sigma. So if I substitute the expression for f of x, I should get 1 by root 2 pi times sigma integration from lambda minus t sigma to lambda plus t sigma. F of x is e to the power minus x minus lambda whole square divided by twice sigma square dx. This is the integration. Okay, and we can integrate this by using substitution of variables. We will substitute the variable 2 times. First, we'll use the substitution. I repeat, first we'll use the substitution z equal to x minus lambda by sigma. And then, okay, and then we'll get this expression as P within T sigma is given by 2 by root 2 pi integration from 0 to t e to the power minus z square by 2 dz. We'll get this expression. Okay. We have calculated the value of this integration minus z square without the factor 1 by 2. So if I want to use that particular formula, then I use the substitution again. Okay. So if I use the substitution again, so let me use a different color now. Let me use blue. So if I use the substitution again, this will reduce to actually 2 by root over pi e to the power, 0 to y, 0 e to the power minus y square dy, where y is actually z by root 2. So in this expression, if z square by 2 is replaced by y square, then we get y equal to z by 2, and this limits it become, this is actually t by root 2. Okay, so if I use if I change the variable from z to variable y by using this substitution, so this is nothing but simple mathematics. I get this expression, this final expression. And if you look closely at this final expression, what is this? This is nothing but the error function. So this is the error function. ERF, error function, t by root 2. This is error function t by root 2 now. So what does it say? It says that, so let me change the color first. It says that if I perform a measurement, okay, and what my question is, what is the probability that the value of that measurement will lie between lambda minus t sigma and lambda plus t sigma? Okay, that probability is given by the area under this curve, okay, integrated between lambda minus t sigma to lambda plus t sigma. And that the value of that integration actually turns out to be the error function of t by root 2. Okay, t by root 2. Okay, so we have obtained this final formula, that is the probability that when we perform an experiment, when we perform a measurement, the value, the observation will fall within t times sigma of the true value lambda is given by this error function. Okay, so now let us look at different cases. That is, if I take t equal to 1, what is p? If I take t equal to 2, what is p? If I take t equal to 3, what is p? So let us look at that. And this will be the last part of today's class. So first, let us take t equal to 1. So let me take a new sheet of paper. So take when t is equal to 1. When t is equal to 1, we have the probability that the measurement lies within sigma. That is A. That is the normal curve. Let us say so the probability that the measurement lies within sigma, that is, it lies between lambda minus sigma and lambda plus sigma. Okay. So this is actually error function. So what did we have in the last slide? In the last slide, the value was error function of t by root 2 pi. So here we are taking the value of t to be 1. Okay. So if I put t equal to 1, we get error function of 1 by root 2 pi. Okay, 1 by root 2 pi. So here we have P within sigma. So that is, we have taken T equal to 1. So here it is equal to error function of 1 by root 2. So sorry, there is no pi. Okay. So 1 by root 2. And if we look at the integration table for the error function, the value of this function, error function, when x is equal to 1 by root 2, this actually turns out to be 0.6827. Okay. And what does it mean? It means that nearly 68% of the measurements lie within one standard deviation of the true value of measurement. Sini ko ako'y ngarang 1 sigma lorgadi, 1 sigma lorgadi 68%. It actually comes out from this. Okay. And now if I take t equal to 2, okay, so when t equal to 2, we have p within 2 sigma. This is error function 2 divided by root 2. So this will be error function of root 2. And when we calculate this error function root 2, or when we check the value from the integration table, this actually turns out to be 0.95, 0.9545. Okay. So if we take the limits that is between, this is lambda minus twice sigma to lambda plus twice sigma, the area under the curve is approximately 95%. So sini ko ako ngarang haigibda 2 sigma oirgadi 95% oi haigibdo. Ngarang haigibdo sini ko. The meaning is here. Then let us take when. So let me take a new color here. Right. So when t equal to 3, we have p within 3 sigma, that is error function of 3 by root 2, and this actually it turns out to be 0.9973. So what does it say? It says that so here 3 sigma to this Andre matay do or matay dama, here it will be somewhere here. So from this, so this is lambda minus 3 sigma. From that it will go here, cos the lambda plus 3 sigma learning. So lambda plus 3 sigma will be somewhere here. So the area under this curve is around 0.9973. That is 99.7% of the measurements lie within 3 standard deviations of the true value of measurement. So this is what we said, that when we take 3 sigma, we have 99%. 3 sigma or 99%. So it is this 2 sigma or 95%, 1 sigma or 68%. This is how we actually calculate it. So let me pause my recording here.